First of all, thank you all for being here, listening to this presentation. I'm Delio Tolivia. I'm from Talento Corporativo, as she said. I'm in the R&D and I line of the company. So we made a lot of different projects using new technologies like machine learning. The project that I'm going to present you is the optimization of passenger waiting time in elevators using machine learning. First of all, I want to make a small presentation of my company. It's called Talento, Integrating Digital Transformation. And the lines that we work in Talento are very different ones, like training. We design and implement e-learning plans, e-learning courses, etc. We also have custom technology to make e-commerce, mobile apps, webs, CRMs, etc. We make technological innovation, is the line where I'm working. We make projects with IoT, machine learning, blockchain, augmented and mixed reality. And finally, we got a line of digital communication with online presence, digital strategy, digital marketing, content, and multimedia. As I said, in the technological innovation line where I'm working, we make projects mainly with these technologies: virtual reality, virtual, mixed, augmented reality, mainly, blockchain, machine learning, and IoT, Internet of Things. In the last year, we present a project that uses Internet of Things, machine learning, and blockchain. This year, I'm going to present you a project that only uses machine learning. Well, what's the project background of this optimization of the waiting time? The background is that we work with Thyssen Group. They got a lot of elevators in different parts, in cities, in hotels, in office buildings. They got a lot of elevators, and these elevators collect data of their work. They collect the data about the calls of the users. They collect where the elevator is when the user clicks the button, where the click was made, the time that the elevator takes to go from one floor to the other floor, if the elevator was going up, going down, the state of the elevator, if there were failures. They take a lot of data of the work of that elevator. All the data of all of them goes via internet to the one server and a database, and they got an application to control them. They can see in real time how one elevator is working. They can stop it, send it to a floor, see if there is failures. It's a control application, very, very good for all the elevators that they got installed in different places. So this is the start point of the project. So we make this collaboration with Thyssen Group to try to make this optimization of the waiting time of the passengers. Why do we use this machine learning, or how we do use machine learning in this project? First of all, the first point that we have to see in every machine learning project is if we got enough data and quality data of the problem that we want to solve. In this case, we got a lot of data from these elevators. We got data from months of work of this elevator with all the calls of every day of them. We work with Thyssen because Thyssen Group wants to improve the service that they give to the clients. The clients hired to install an elevator. The elevator is standing the street of a city, and they want to improve the service that give to the client of this elevator. So we can use machine learning to predict. And what we are going to predict? We want to predict where is going to be called the elevator, where the next user will call an elevator in the street, for example. In this way, we can reduce or improve the waiting time of that user. So we can make what we call an intelligent elevator. It's an elevator that predicts where to go before the user calls it. that's the project, the main frame of the project, what we want to do with this project. So for starting the work, we have taken data from 5 street elevators. It's elevators that are on the street in one city, and we also have data from a group of 2 elevators that work together in a hotel. This data on this hotel elevator we were talking at the end of the presentation. Now we are going to focus on the street elevators. First of all, we take all the data and we start to make graphics and statistics analysis of this data. We make the data exploration part of the project. As we can see in this graphic is the count of calls in front of the seconds wait, and in color we see the origin of the calls. The origin of the call can be from inside the elevator or from the hall, from the outside of the elevator. We also have an NA kind of type that is when the system can detect where the call came. There got some failures in the recollection of data from the system. As we can see in this graphic, we see that 4 of the elevators have a very similar behavior. Is the first 4 of them, and they got a very, very different one is the 5. So we make 2 groups, one group with the 4 first elevators and one group from this elevator that's in the right of the graphic. Mainly the difference is because the 4 first elevators are 2 floors elevators. Meanwhile, the 5 elevators have 4 floors. That's a very, very different behavior in the elevator. We keep on exploring this data, and we see that the first group also have little differences between them. As you can see, the first one is also the count of the calls and in front of the seconds wait. We only focus on the whole calls, because if we want to improve the waiting time of a user, there's only the whole calls that count for that. We don't need to analyze the calls to the elevator made inside the elevator. And in the right graphic, you can see a box plot of the same data of the elevators. As we can see, there is 2 subgroups. One of them that we label 1-4 is the top in the left graphic, the top one and the bottom one, and another subgroup is what we label 2-3, that are the 2 elevators in the middle. We see that it's a little difference between these 2 subgroups of elevators, as you can see in the graphics. Well, keep on with the exploration of the data. We take the subgroup, the subgroup of the elevators that it's in the middle in the previous graphic, the one we labeled 2-3, and we make these graphics. We count the calls in front of different variables. The most important one is on the left bottom part of the graphic. That is the end floor number. The end floor number variable tells us where the user makes the call to the elevator. Over it, it's a start floor number that is the floor where the elevator is when it's called. And there at the right, there's another variable, like if the elevator was going up, it's stopped, it's in service, or is failure. There's different variables that this doesn't tell us much information about the problem. The more important of this graphic is the end floor number. In this subgroup, we detected that all the calls came from the floor 0. It's a strange thing that we detect with this data exploration. In another subgroup, the subgroup that we label 1-4, we realize, if you see in the graphic, the bottom left part again, that mainly the 90% of the calls also came from the floor 0. It's here there is calls from the floor 1, etc., but it's mainly the 90% of the call came from that floor. Finally, the different one, the elevator that behavior is more different, the one we label with 5. As you can see again, the left graphic in the part where in floor number, we see a distribution of calls between the floors, mainly from floor 0 and floor 2. And in the right, we see the seconds weight and the count of calls for every floor. And we see that's a very more complicated distribution of the behavior of the elevator. Also, in this data exploration, we studied another variables like time distribution by hour, day, and week. We see some things like in Saturdays, there's a reduction of the number of calls to the elevators. It's very clear in the left graphic. I see these downpegs of the graphic, and we also see in the right bottom of the slides, the graphic, we see by hours that the elevators is less used in the night till the 8, 9 in the morning, where the count of calls is starting to grow to a top that stands more or less stable from all the day till late in the afternoon, where the calls started to go down. This is the behavior of all of these straight elevators. It's very similar for all of them. Well, taking all this information that we analyze and thinking what we are going to do with all this, we try to make these solutions. For this subgroup 2-3 that add the elevators that got all the calls from the floor 0, we decided to establish a thing that this group called a parking at floor 0. This is a functionality that got their control application that works in a way that if an elevator is stopped in a floor for 30 seconds, 1 minute, you establish the time, the elevator in an automatic way goes to the floor 0. This, if all the data that we got is true, this will make all the elevators to go to the floor that all the calls are made. So this is a very good solution. In the second subgroup, the one we lab with 1-4, we also got a 90% of the calls to floor 0. We think that we are not going to make a model that can predict these calls better than sending the elevator to the floor 0 with this parking functionality. We make all the elevator to go to floor 0 in the same way as the first one, and in this way we know that we are going to predict the 90% of the calls of the elevator. So we don't have to make a machine learning model for that group. And finally, the one that's more complicated, the one we label with 5, in this, yes, we decide to make a machine learning model because his behavior is very more complicated than the other ones. Results for the two first subgroups. In the one that we made the parking at 0 and all the calls came from the floor 0, we detect that there is a malfunction in this group of elevators, because the ThyssenKrupp personnel goes to the elevators because they don't think that all the calls came from the 0 floor. So they go there, start to see what happened, and they see that there is calls from the floor 1, but they are not recorded in the database. There's a problem in the collection of data from that elevators. So we think that this is a success of the project. With only the data exploration part of this project, we detect some failures in the collection of data for that elevators. In the other subgroup, the one we label with 1-4, that 90% of the elevators came from the floor 0, we achieved an improvement of 12% in terms of reducing the waiting time for the users. It's a very good reduction time of the waiting time for the users of the elevators. In this case, we also have sensor to measure the consumption of energy of the elevator, because we don't know if making this parking at floor 0 will consume more energy than left the elevator as it was before this project. With this measure, we confirm that there is no more consumed in the solution that we propose. So this again is a success of the project. We can reduce 12% of the waiting time for the users with no extra cost of energy for the elevator. I want to say that this is the most important of this part of the project. Is the data exploration. The data exploration is very, very, very important. As you can see, only with this part of data exploration, we can make two very good results. We detect failures in the record of the information from the elevators, and in other group, we can improve 12% of the waiting time for the users. We don't have to use machine learning till now, till this point of the project, and we got two success. Well, entering in the machine learning part of the project, we have taken all the data and create some models using the OptiML option of BigML. We get different algorithms and different tests with these models, and we start to improve them with feature engineering. We create new variables to improve these models. We create some variables like seconds wait 1. That's the second that the user have to wait in the previous call. Another one that we used was last hour calls 2. That's the number of calls from the second floor in the last hour. To remember in the graphic, the second floor is one with largest number of calls. And last 3 minutes call 0 is the number of calls from the floor 0 in the last 3 minutes. These are the variables that improve the model. We also try with different variables of this kind, like the number of calls from the first floor in the last hour, the number of calls from the 0 floor in the last hour, different ones, but they don't improve the model. But these three variables, yes, they improve the model. We also try to add data from the work calendar or methodology of the city where the elevator is. We think that this data will make some improvement in the models because there are elevators that are on the street. We think that if it's raining, the people will use more the elevator. So maybe they got a relation with the use of these elevators. But all this information doesn't improve the models. The methodology data maybe will be better if we get information by hour, the precipitation in every hour of a day, but we got data from all the day. So maybe we can improve more the model, getting more precise data of meteorology. The best model that OptiML give us and all this feature engineering and all we do was an ensemble. For selecting the best model to use in our project, we focus on accuracy. We want that there is no difference between the floors, and we want the most precision in the prediction of the floor. So we focus on this parameter of accuracy. We get a model with a 53.4% of accuracy. It's not a very good one, but we think that may work, reducing in some way the waiting time of the users of the elevator. How we implement this solution? We have put into production a Docker containing an API, the elevator control application, the one that I tell you that Thyssen have controlling all their elevators, make calls through this API, and he get the probability of each floor for the next call. Then the system can choose the best option to move the elevators. There is a set of different conditions that this system have to use, like if the probability of the two floors are over 50%, then make the elevator go to the floor of the first. If the probability of the first is more than 20% than the second one, etc., etc., etc. We make a set of rules of how the system have to act in front of the prediction that the model made. All these rules are in the control application of TSEN. You only focus on the API and the model that we integrate in this Docker. The technology that we used was Docker, MongoDB, and Node.js to make this application. Well, the results of this model. When we are going to test the model in this elevator, we detect that the elevator was out of service and we couldn't use it. The elevator was out of service for 2 months. It's a very, very failure or very hard failure of the system. We can't try our model in the elevator. And that's when we decided to use the data that we got from the hotel elevators that we name at the beginning of this presentation. We decided to try the same model with the same variables that we got for the street elevator in the hotel elevator. We take the new data from the hotel elevators, train the model, and implement it in the Docker and make the test in the real world. At first, we think that this is not going to work very fine because the behavior of an elevator in the street will be very, very different from a group of 2 elevators that work together in a hotel. That's very, very different. We think that there is not going to be a very good result of this model, but we want to try because I think that I'm going to tell you afterwards. For our surprise, we achieve an 8% of improvement in the waiting times. There's a very, very good results in reducing the waiting time of the users of the elevators in the hotel. However, as I said before, the model isn't perfectly designed for this group of elevators. We have to improve it, making this data exploration, feature engineering, specific for this group of elevators and how they work together, adding new variables and testing these things. One of the things that we want to make this test with a model that isn't made specifically for the hotel elevators is because when we are going to put this into the real world and make it a service of TSEN group, we don't want to take every elevator that they install. We have to make the data exploration, the model train, the selection of the good model, the feature engineering for every elevator. We want to make not one model for all the elevators, but maybe we can take and make group of elevators: street elevators, hotel elevators, office elevators, building, people building elevators, etc. We make 4 or 5 groups of elevators and use the same model and variables for every group. This will be a very nice way to reduce cost of making these models and a very good way to make models very fast. TSEN can install an elevator, make it work for 2-3 months, recollect the data, train automatically the model for that kind of elevator, and put it in production working immediately. So this is also.
1 second, Delio. You should start wrapping up because there are only a couple of minutes to go until the end of your.
Okay. I finish now. Well, this is a very good result of the project. So what's next? We want to keep on working with this elevator, improving the model, and we have another use cases like predictive maintenance, product planning, quality control, demand forecasting, etc.